separators again. Another example for separators. Again, let us focus on grid graphs. So, as I said, we're working with grid graphs here because it's easy to imagine and find a separator there in a grid. But all these things can be generalized to an arbitrary data graph. So let's assume that we have our graph looks like a grid. We have like a weight. So yeah, these things are edges and they all have some weight assigned. And the second example would be a data structure for answering distance queries. So the task is like, build a data structure so that can answer queries like, what is the distance from U to B? So this is, the graph is undirected, weighted, and well, the queries should be answered faster than linear, and preprocessing should be faster than squared. So I suggest you first spend like a couple of minutes thinking about how can you build a thing like that, and then we'll discuss. Yes, it's a grid. N is the size of the entire graph. So this thing has root n by root n. The size of root of the vertices. Okay, so let me give you some hint. The first problem I'd like to consider is, given a grid graph, okay, so the upper half and the lower half. So assume that we're only interested in questions in which U is in the upper half and V is in the lower half. So we'd like to find the distances between you guys up here and down here, right?
My idea is to find the separator in the middle that we draw the
Basically, the middle row, right?
Yeah. So suppose I take this row here. So I do a taxa for every vertex.
Yeah, I think these were vertices. Like vertices, I think.
Oh, sorry.
Yeah.
So I take this vertex here, and for every one of them, I do a taxa up and down to get the shortest path for every vertex. And then I have now two graphs. And we can like see the separator like a node in a binary tree. Then we do another separator here.
Yeah, I mean, you're solving this one, right?
I'm solving the like. No.
Can you start with like this case?
What?
This like upper and lower, right?
Yeah, this is the first separator. I do.
Okay.
Okay. Then after reading the first separator, this upper graph and this lower graph. And then I do the same thing and build a separator here and do the action for each side. And this will like be another node in a binary tree. And for the side we do the same thing. And it will start looking like a KD tree. And now we want to find the shortest path from one vertex to the other. So let's say the first vertex is here, and the second vertex is here. We'll find this common accessor, that's this one. And let's say that one vertex is here and the other is here. And let's put here. So the separator is this one. And we then, for every vertex on the separator, we find the shortest path from here to the other vertex. And my solution might be something like this. But what if the solution is like here? So you go up, and for every ancestor, do the same thing.
Yes, this works. Right, so the general idea here is to, if we have a grid like this, like, assume a very special case that we have some graph, single node here, and some other graph down there. So if you want to find distances, if we want to answer queries like, what is the shortest distance from a guy here to a guy here, right? So then, and there is a single vertex that separates that. So then what we might do is to find the shortest distances from this guy to every other vertex in the graph. And now, so, I don't know, let's call this vertex S. So dv would be distance from S to V, and that's U. So in order to find the distance from V to U, well, the shortest path, this path has to go to S with the shortest path possible, and then it has to go to U, again, with the shortest path possible. So du plus dv is the length of the shortest path between V and U. Now what happens here is actually almost the same, but there are multiple S's possible, right? So we take the whole row, and for every vertex in this row, we compute distances to every other vertex in the graph. So now we have distances from this guy, and so on. And now, if you'd like to find the distance between U and so V here, then obviously the shortest path has to go somehow through this separator. Might go like this, might go multiple times. But obviously there is at least one vertex of the separator which the path is going through. And for this vertex, well, we can find, we know the shortest path from here to U, we know the shortest path from here to V, and putting together those shortest paths creates the shortest path from U to V. Now, we're going through all vertices, so for some vertex, we might get some path which is different and it's not necessarily shortest, but we go through all vertices and select the global shortest one. And the claim is that this would really give us the shortest path from U to V. Make sense? Cool. So this is for U and V in upper and lower half. And now, once we do that, we remove the separator and recurse. So, okay, we've taken care of all pairs like upper and lower half. And now we cut the graph into two pieces. And we do exactly the same thing in this upper half and then lower half. We find some separators and we repeat the construction. Now, when we get a query, we take a look at the structure of our algorithm. So we have U here and V here. Like this. U here and V here. So our algorithm found some separator. So we do this, and for every possible vertex of the separator, we check what's the concatenation of the path to the separator and the other side. And we get some candidates for the shortest path. And then we recurse on the side in which they both belong, right? Now we have this graph, and in which we found the separator like that. So we go, again, through all vertices here, and try to build paths that look like this, right? Go through all vertices and then check the shortest path. And then at some point, okay, and then we recurse on the side of the separator which contains them. And then at some point, we get a graph in which U and V get separated. And then, again, we examine all vertices in the separator, and we know that the shortest path from one guy to the other that goes through the separator, we check all of them, And then this way we check all possibilities, and we're sure that what we found is the shortest path. Okay, so what's the running time period? So it's actually, I think we'll get the formula like there. So at the first level, we need to compute root n times shortest paths. So it's n log n plus, after doing this in the first level, we recurse on the upper and lower half, so it's twice the running time of a problem which is 2 times smaller. So yeah, we've got this one before, and this solves to n root n log n. Now the query time is it's root n on the first level, on the top level. And then we because we have to check the root n options, and then we've got a graph which is 2 times smaller, so it's root n over 2. Then it's root n over 4, and so on. So it's like a sum of root n over 2 to the I power, which is I. This is root n times sum of 1 over root of 2 to the I, which is equal to root 2 to the I. So this again converges, and this is root n. Right? So we build a data structure in this time, and it allows us to answer distance queries in root n time. Any questions regarding this? Cool. So let's see. We have 10 more minutes. And we should start lunch. Okay, so I believe we're going to start the next topic this time. So let us recall what happened here. So the second technique for planar graphs is separation. And separation is a way that is a technique that enables us to divide and conquer, right? So again, this is a technique that maybe does not give us additional power in terms of what we can compute, but allows us to compute certain things faster. So of course we can, this problem can be solved with a very simple algorithm, but it just would be much slower. And this allowed us to speed things up. But the kind of thinking that you need here is divide and conquer, right? So if we can solve something for a separator and then solve something recursively for the 2 parts of the graph, then in planar graphs we might use the separation technique and then get some gain. I think we're gonna stop here. So since we stopped a bit earlier, I suggest we now go for lunch, and then let's meet in the labs maybe 1:45. That's because we're going to have the first contest today, and this would be on our contest system, and I'd like you to have time to create your accounts and get familiar with the system. The contest is scheduled to start at 1, so yeah, we'll have to be there earlier in order just not to be late for the start. Okay, that's it for now, and see you after lunch. Thank you. There's also algorithms try and draw graphic relationships and I do really like drawing things like this and so on. And at some point, the algorithm goes like, well, at this point, you should be able to do this, otherwise you don't see that graphic. Oh, so you're algorithm, right? So, the algorithm can be implemented even to run in linear time, but it's not easy. It's quite a complex. I mean, lecture can describe Yes. So usually what happens, there are two options. One of them is that you get coordinates of points. So you get just a graph, but you have the drawing, right? So you can say this vertex is at this point, and so on, and you can assume that you can connect in such a way that the edges don't cross. That's one way of doing it. And the other way, which seems to be more difficult, but also this sometimes very useful, is that you get this picture but in a slightly different way. So you get a vertex, and then you get its neighbors, but in a sorted order, like a circularly sorted. So you know that these are the consecutive neighbors around it. And this thing is especially useful if you like to, because you can different faces of the ground. You have a vertex. So what you can do is you can go along an edge, get here, and you know what is the next edge in order. So this one, so you can go along. Then you get this vertex, you can find this edge, right? So this edge, and then this edge, and you can find the face. I think there are two options. I mean, in problems, I think it is okay. It's often that it's not a grid, but a grid with missing edges. Because grid is, so then it's a bit more complicated. One important reason to notice is that sometimes you don't even need to know what is the structure of the graph. Like with the vertex of the 3-5 trick, right? You don't really need the structure of the graph. You just need to know that if you know that it's planar, you know that there is a vertex of this 3. And you're, like in the other, you're not using the drawing at all, right? You just